Question 1. A spring has a spring constant K of 82 newtons per meter. How far must this spring be compressed to store 35 joules of potential energy? Okay, so we have potential energy formula, half kx squared. And it looks like we are just solving for x. So do the algebra. Multiply by 2, divide by k, square root. And I'll put in the values. Okay, then we'll go to the calculator. And I'm getting 0.78 meters. So that's how much the spring needs to be compressed. Question 2. A 5.0 kg monkey swings from one branch to another 1.5 meters higher. What is the change in gravitational potential energy? So the change of gravitational potential energy is delta U equals U2 minus U1. So we'll have the monkey swing here to, let's say, here. So I'll set the reference height at the bottom. I set the reference height at the bottom, then U1 becomes 0. So now we'll just have mgh2. And we have all the values, 5.0, 9.8, and 1.5. Okay, so calculator time. And I'm getting 74 joules. Number 3, by how much does the gravitational potential energy of a 58 kilogram pole vaulter change if her center of mass rises about 3.8 meters during the jump? All right, so same as the monkey question, I believe. So we'll have the pole vaulter, track and field question, by the way. Gotta love that. They'll start here, and they'll go whoop, and they'll end up here. So we'll make the height equal to 0 where they started from. So change of gravitational delta U is U2 minus U1. U1 will be 0 again. So it'll just be mgh2. So they are 58 kilograms, 9.8 for G, and the height given was 3.8 meters. Okay, so to two significant digits, I'll have 2.2 times 10 to the 3 joules. 4. A 66.5 kilogram hiker starts at an elevation of 1,500 meters and climbs to the top of a 2660 meter peak. A, what's the hiker's change in potential energy? B, what's the minimum work required by the hiker? C, can the actual work done be greater than this? Explain. Okay, so part A is the same as before. So we'll have the mountain. The hiker will start here, which is 1,500 meters high. And they'll end at the peak, 2660. So why don't I just make the reference the bottom of the mountain? So delta U is U2 minus U1. It'll be mgh2 minus mgh1. And if you factor out mg, you get mg times h2 minus h1, which is delta h, actually. So Kind of a shorter way to write this is mg times delta H. Okay, so the mass is 66.5, G 9.8, and the delta H is the difference between 2660 and 1500. Okay, go to the calculator. Okay, so 755,972, that'll be to two significant digits due to the 9.8 joules. So that's how much, that's the change in gravitational potential energy. So if they're going to gain that many joules, then at least that much work will have to be done. At least that much work will have to be done. So the answer to part B will be the same answer. Now, can they do more work than that? Yes, they can do more work than that in a variety of ways. So work, for example, is force times displacement. And if they apply the minimum amount of force, then they can do the minimum amount of work. But if they're like really applying a lot of force to get up there, they'll get there a lot faster. But the displacement doesn't really depend on time. Okay, so they can apply a ton of force, get there really fast. Work is still force times displacement. And in that case, if they use so much force, they're going to end up doing more than the minimum amount of work. Five, in starting an exercise, a 1.7 meter tall person lifts a 2.20 kg book off the ground, so it is 2.40 meters above the ground. What is the potential energy of the book relative to the ground, relative to the top of the person's head? And C, how is the work done by the person related to the answers in parts A and B? All right, so interesting. So I'm going to draw a diagram because I don't know what's going on. I'm just going to have to clear this up with a diagram. So we have a person, 1.70 meters. And they lift a book from the ground. So there's going to be the book. And they lift it so that it is 2.40 meters above the ground. Okay, so this will be T equals 1, or sorry, T1. And then when they lift it higher, it'll be somewhere up here. This will be time T2. So that is, the whole thing is 2.40 meters. Okay, so let's see, what are they asking here? A, what's the gravitational potential energy relative to the ground? Okay, so mgh, but we're doing relative to the ground. That will tell us what h is. So the mass of the book is 2.20 kg, kind of a heavy book. Must be a physics textbook, times 9.8. And the height relative to the ground that the book was lifted, 2.4 meters. Okay, so I'll multiply that. So 51.744. I'll just round that to two significant digits, 52 joules. B asks us for the gravitational potential energy, but relative to the person's head, the top of the person's head. So relative to the 1.70 mark. So in that case, the height relative to the top of the person's head is only this much height here, which is 2.40 minus 1.70. That is 0.70. So I'll put 0.70 in for the height for part B. Okay, so we're getting 15 joules. Okay, now what's going on with C here? Let me read this again. How is the work done by the person related to the answers in parts A and B? How's the work done by the person related to the answers in parts A and B? Well, the person, I think, lifts it from the ground to 2.40 meters high. So, I mean, the work done would be at least 52 joules, if you ask me. So they did at least 52 joules of work. And it's at least, that's the minimum. And the reasoning is the same as the mountain climber question previously. That's just the minimum. They could apply a really large force, more than the minimum force required, to do more work than 52 joules. All right, so now we do question 10 to 19. Okay, number 10. Jane, looking for Tarzan, is running at top speed of 5 meters per second and grabs a vine hanging 4 meters vertically from a tall tree in the jungle. How high can she swing upward? Does the length of the vine or rope affect your answer? All right, so there's the vine. It's going to swing and end up at some kind of a max position. So I'll call this T1 and T2. I'll make my reference at the bottom. And we have to find how high they swung at T2. So this is a conservation of mechanical energy. At the bottom of the swing, 0 gravitational because I set the reference height there. At the top of the swing, kinetic is 0 because they are instantly at rest at that moment. So the equation simplifies a little bit. Half mv1 squared equals mgh2. The masses cancel, divide both sides by mass, and we are solving for the height. So then we will just divide by g to get h2. I'll put in the values. So the speed was 5.0 squared over 9.8. Okay, calculator time. I get 1.3 meters when rounded to 2 significant digits. Does the length of the vine or rope affect your answer? So they told us the vine was 4 meters long. So no, I don't think the length of the vine affects it. It could be longer, it could be shorter. The only thing is, like, the vine has to be at least half of 1.3, so it has to be at least 65 centimeters long, because if it was 65 centimeters long, like, it has to be able to get to the height of 1.3. So it would make a full half circle swing and get to a height of 1.3. If it was shorter than that, it would not be able to get to a height of 1.3. (11) A novice skier starting from rest slides down a frictionless 32-degree incline whose vertical height is 105 meters. How fast is she going when she reaches the bottom? Okay, so I'm going to draw myself a picture. I'm going to have a 32-degree incline. It's 32.0 actually, they say. The vertical height was 105. How fast is she going? Started from rest. So here, T1 started from rest. Gets to the bottom, T2. How fast are they going? So I'll set my reference height at the bottom, h equals 0. And this is a conservation of mechanical energy. There's a normal force, which is non-conservative, but it's always acting at 90 degrees to the motion, so it does not do any work. All right, it starts at rest, K1 is 0. I set my reference at the bottom, so U2 is 0. So we're getting mgh equals half mv squared. Both sides, we can divide mass on both sides, and we will square root to get v2. After multiplying by 2, that is. Okay, square root 2gh. H is 105. Okay, calculator here. .45 when rounded to 2 significant digits, meters per second. All right, so the 32-degree angle did not seem to come into play there. Does it come do they refer back to this question later? And we do something with the 32-degree angle? I don't know, we'll see. We'll go to question 12. A sled is initially given a shove up a 25.0 degree incline. It reaches a maximum vertical height 1.22 meters higher from where it started. What was the initial speed? It's kind of like the reverse of the previous question. We have this 25-degree incline. It reaches maximum vertical height. Let's just say at the very top of this thing, 1.22 meters high. So this looks the exact same. So U1 plus K1 equals U2 plus K2. So at the maximum height, it comes to an instantaneous stop. K2 is 0. Set to h equals 0 at the bottom, so U1 is 0. So same equation as last time. Half mv squared equals mgh. Divide the m's. Multiply by 2 and square root. Okay, to 2 significant digits, getting 4.9 meters per second. That was the initial speed after the push. Okay, 13. In high jump, another track and field example here. The kinetic energy of an athlete is transformed into gravitational potential energy without the aid of a pole. With what minimum speed must the athlete leave the ground in order to lift his center of mass 2.1 meters and cross the bar with a speed of 0.7 meters per second? Okay, so person can start here and they jump over the bar here. So we'll call this T1, T2. And they want a speed here of 0.7 meters per second. And they want it at a height of 2.10 meters. That's pretty good, actually. That's very good. I'll set the h equals 0 at the bottom there. All right, so U1 plus K1. As for ignoring air resistance here, non-conservative force. Okay, here only one thing cancels out to 0, the starting gravitational, because I set h equals 0 there. And so then half mv1 squared equals mgh2 plus half mv2 squared. And the m's, every term has an m. We can divide both sides by m. I'm looking for the initial speed, so multiply by 2 and square root. So when I multiply by 2, I'll get 2gh plus v2 squared. 2 times half is just 1. And then we square root both sides. So let's put in the numbers. Calculator. And I am getting 6.5 meters per second. (14) 75-kilogram trampoline artist jumps vertically upwards from the top of a platform with a speed of 5 meters per second. How fast is he going as he lands on the trampoline? 2 meters below. And to give you a nice diagram there. B, if the trampoline behaves like a spring of constant 5.2 times 10 to the 4 newtons per meter, how far does he depress it? All right, cool. So let's draw this picture here. So we have the platform, and then the trampoline is 2 meters below it. There's a trampoline. So here, it's a 2 meter difference. Okay, the person will be here, T1. They're gonna jump up, and then presumably, it says vertically up, but he has to go forward at least a little bit so he doesn't land back on the edge, but I guess that's a negligible amount. So he's gonna land on the trampoline, T2. Okay, so he jumped up at 5.0 meters. No, yes, 5.0 meters per second. Okay, so part A is to find the speed at T2. So conservation of mechanical energy. So let me say h equals 0 right at the trampoline. So U2 is 0. And then mgh1 plus half mv1 squared equals half mv2 squared. Cancel out the m's. Multiply by 2 and square root. So 2gh1 plus v1 squared, all square rooted. That'll equal v2. Okay, calculator. So 8.0 meters per second. All right, so that's part A. Part B is how much they compress the trampoline by, assuming it behaves like a spring with a constant of 5.2 times 10 to the 4 newtons per meter. Okay, so if I draw a new diagram, well, I'll just add to the other diagram. So they're gonna compress the trampoline. It's gonna go boing, and okay, compress the trampoline. So we'll call this T3, yeah, T3, just to keep things distinct. So I'm gonna go conservation of mechanical energy between T1 and T3. All right, so I could have done T2 to T3, but if I use T2, then I'll be relying on this rounded number of 8.0. So if I don't want to rely on a rounded number, I'll go with T1 and T3. So we'll have UG1 plus U spring 1. There's two potential energies now, gravitational and spring, and then kinetic, equals UG2 plus US2 plus K2. All right, at the maximum deformation of the trampoline at T3, it comes to an instantaneous stop, so there'll be no K2. The trampoline is not compressed at all before he even jumps, so spring 1 is 0. All right, so now we'll go mgh1 plus half mv1 squared equals mgh2 plus half kx squared. Now there's one thing we need to, one very important key here is to recognize that the amount that the spring stretched by, which is x, is going to equal to negative h3. Okay, so it goes down. So h3 is a negative number because it's below the reference. X is a positive number, though. X is the amount that the trampoline deforms by, which is a positive number. So x has to be negative of h3. Okay, so h3 is negative, but a negative of a negative is positive. So x has to equal to negative of h3. Actually, in my solution here, these need to be 3s, not 2s. Okay, so the key is x equals negative h3. Now, if you didn't realize it was negative h3, if you just wrote that it was h3, will luckily be okay still, I think, because it gets squared. X gets squared in the equation. So it becomes positive anyway. Okay, so let's go mgh1 plus half mv1 squared equals mg Why don't I do this? Why don't I, h3 will equal to negative x. And here I'm going to change h3 to negative x. I'm going to see what happens when I do that. All right, this looks like a quadratic formula coming to me, so let me plug in some numbers here. The trampolinist is 75 kilograms, 9.8. H1 is 2 meters. Okay, so times half, 75. V1 squared, so 5 squared, equals negative 75 times 9.8x plus half 5 52,000 5.2 times 10 to the 4 x squared. Okay, so some calculator work here. 75 times 9.8 times 2 plus half times 75 times 5 squared. So the left side of the equation is 2407.5. The right side of the equation, so negative 75 times 9.8, 735, x plus half of 52,000, so 26,000 x squared. So that's going to be a quadratic formula thing. So just remember, you have to, or you probably should, put things in a standard form, like if this were a test. And then we'll quadratic formula it. Now I'm just going to use the computer to quadratic formula it. All right, so let me type that in. On a test, unfortunately, you'll have to actually do the whole quadratic formula with these kind of annoying numbers. Okay, so getting answers, I have a negative one, which is going to be inadmissible. But I also have a positive one of 0.32. Okay, I'll box that, inadmissible. Okay, you guys are welcome to check all of that for errors and let me know. We can add to our tally. 15. A 60-kilogram bungee jumper jumps from a bridge. She is tied to a bungee cord 12 meters long when unstretched and falls a total of 31 meters. Calculate the spring constant of the bungee cord, assuming Hooke's law applies. Calculate the maximum acceleration experienced by the jumper. Okay, so I'm going to need a diagram for you here. So we'll have the jumper start here. Okay, T1. They're going to fall 12 meters. So here, there's the 12-meter mark, or the length here is 12 meters. And at this point, the bungee cord begins to stretch. So there's no stretch to this point. But after this point, it will stretch until it gets to 31 in total. So T2 will be down here. 31 in total, so if the first part's 12, the other one is 19. All right, so I think that's what's going on. Okay, so I'm going to go conservation of mechanical energy. There's gravitational and spring and kinetic on both sides. Some things hopefully will cancel out to be 0. Okay, so this is kind of awkward because it says they jump off, which assumes that there's a kinetic energy because they jumped off, but I don't see how we could solve this unless kinetic started at 0. So let's just say they should have like stepped off, very slowly jumped off. So it's pretty much 0 joules of kinetic energy there. We'll give reference location. I think it may be wise to have the 12-meter mark as a reference location. That's just a gut instinct. We'll see what happens. Now, when we do that, we don't have any zeros for gravitational 1 versus gravitational 2. At the very bottom, T2, when the bungee cord is stretched the maximum amount, they're going to be at an instantaneous rest as well. So both K's will be 0 in this case. And then at the beginning, the bungee cord has not been stretched at all, so that'll be 0 as well. All right, so out of the 6 terms we started with, 3 of them are 0, so we just have 2 terms here. So UG1, so MGH1 will equal MGH2 plus half kx squared. Now, again, similar to one of the previous questions, x here, the amount the thing is stretched by, is going to equal the same as negative h2. Yeah, so the height of h2 is a negative number. So if we multiply by -1 to turn it to a positive number, that can be our x value, how much the thing is stretched by. This might do the same as, or yeah, let's do the same as last time. Let's say negative x equals h2, and I'll sub it into that middle term there. So we'll have mgh1 equals negative mgx plus half kx squared. And it looks like we got a quadratic formula thing going on again. All right. Numbers 60, 9.8, 12.0 equals negative 60, 9.8 x plus half. Oh, we're solving for k. Oh, wait. I didn't have to do all this because I know the number. Huh, I lost sight of things here. Okay, so 19 plus half k, 19 squared. And we're solving for k. All right, so let me calculate some of these things. Left side, 7,056. First term on the right side, negative 11,172. And then plus half of 19 squared, 180.5 k. Okay, so k is going to be 7,056 plus 11,172 divided by 180.5. So sig digs wise, okay, 2 digits, 2 digits, 3 digits. So adding puts us to the thousands column, which will be 2 digits. So, okay, 2 digits. So it's 101, but I'll just underline the 2 digits, newtons per meter. Okay, so that'll be the answer to A. Now B, find the maximum acceleration. So the maximum acceleration is going to be at the very bottom. Okay, max accel. Because that's when they're going to experience the greatest net force. The net force is a combination of the gravitational force and the spring force. But the gravitational force is the same. It's mg, no matter where the person is in the fall. So the gravitational force is the same for the whole journey. So the only thing that's going to affect the acceleration would be the maximum acceleration would be when it's stretched the most, the largest spring force. So that's at the very bottom. So we'll calculate the maximum acceleration there. I'll get a free body diagram for T2. So we have gravity, Fg, which is mg. And then we'll have the spring force, Fs. It's going to equal to Ks. So the acceleration, magnitude of it at least, will be the net force divided by the mass. So it's going to be the spring force, Kx, subtracted by the gravitational force, mg, all divided by the mass. So we'll use our K from before. The x is 19. Okay, the mass is 60, and then g, 9.8, over the mass of 101 times 19 is 1919 minus 60 times 9.8, 588. So I'm just double checking that the net force at the bottom is actually larger than the net force during free fall. And it is. 1919 minus 588 is like 13 something. And that's definitely more than 588. Okay, so we're going to get the right answer here, I hope. Getting 22 meters per second squared. Up. All right. 16. So they give a picture of a roller coaster. And they're assuming no friction. And they just identify 4 locations on the roller coaster, and they want the speed at all the locations. The first one location, they tell you it's at rest. So I'm not going to take the time to do all the locations. I'll just do the first one. Okay, I'll just do B. All right, so from A to B, there's a 30-meter difference in height. So I'll set the reference down at the bottom there. And it's frictionless, so we have conservation of kinetic energy, of mechanical energy. Okay, so released from rest, U1 is 0. No. K1 is 0. I set the reference height at b, so u2 is 0. So we have mgh equals half mv squared. The masses cancel. Multiply by 2 and square root, getting root 2gh. Okay, so we got 24 meters per second. All right, so at the other points, finding the speed is very similar, so I don't think I'll go over those. So, 17. A vertical spring, ignore its mass, whose spring constant is 900 newtons per meter, is attached to a table and is compressed down 0.150 meters. What upward speed can it give to a 0.300 kg ball when released? And B, how high above its original position will the ball fly? All right, let's draw a diagram here. So we'll have a spring. The constant is 900. And we'll have the ball on it. So I'll call that T1. And right now it's compressed down by 0.1. Okay, so I'm going to make a better diagram. This will be the spring with nothing is on it. So this is the natural length of the spring. Now we're going to put a ball on it and we're going to squish it down. Squish it down by 0.150 meters. And let's call that T1. Now, what upward speed will it give the ball? So, actually, right here, boing, the ball gets launched, and we'll give that T2. And then part B of the question, how high above will the ball go? So the ball will go somewhere up here. So I'll call that T3 in preparation for part B. Okay, but for part A, it's from T1 to T2. We'll have conservation of energy. So it's got gravitational and spring potential. Okay, so release from rest. Need a reference height. So just keeping in mind that we're going to have to go up to T3 eventually, I think it's wise to have T2 be where the height is 0. So UG2 is 0. Also, the spring has been back to its natural position. So US2 is also 0. All right, so MGH1 plus half KX1 squared equals half MV squared. Okay, and we're finding V, so we'll multiply by 2, divide by M, and square root. So multiplying by 2 and dividing by M makes it 2GH1 plus kx1 squared over m, and then square rooting. Okay, so there's the algebra. Okay, h1, it's negative. It starts below my reference line, so negative 0.150. K is 900. X1 is 0.150 squared, because it was compressed by 0.150. And then the mass, 0.300. Okay, so let's work this out. 2 times 9.8 times negative 0.150 is negative 2.94. I'm adding 900 times 0.15 squared divided by 0.3, 64.56. Okay, now I'm square rooting all that. Error. What did I do? Okay, try that again. Okay, so 8.035. I honestly did not think too hard about sig figs. I'm just going to guess that it's 2. All right, so that's the speed it gets launched at t2. But then they want to know how high it gets above the original. So for that, B, I'm going to use T1 and T3. I'm going to use T1 and T3. Again, I could have used T2 and T3, but T2 contains a rounded number for the speed. You know what? I think I'm going to do it anyway. I'll use that rounded number. So I'll go T2 and T3 here. So UG2 plus US2 plus K2 equals UG3. I want more zeros to start with, so I'm going to do this. All right, so UG2 is 0 because I have my reference right at T2. The spring is not doing anything at T2 or T3. Cancel both of them out. And it comes to a momentary rest at T3, so K3 is 0. Yeah, that's why I want to use T2 and T3. All right, so half mv squared equals mgh. You get a simple kind of formula there. The masses cancel. So just dividing by g. So 8.035 squared, 9.8. Getting 3.3 meters. Okay. Nice question. 18. A 0.40 kg ball is thrown with a speed of 10 meters per second and an angle of 30 degrees. What is its speed at its highest point? And how high does it go? Using the conservation of energy. For part B, using the conservation of energy. For part A, I'm using projectile motion. So as a diagram, you have this ball. It's 10 meters per second at a 30-degree angle. 30 degrees. So what's going to happen is it's going to go in projectile motion. So it's going to make a parabola. Okay, parabola, and it's going to have some highest point here. Now at the highest point, if we think back to projectiles, the y velocity is 0 meters per second, and the x velocity is going to be constant. It's going to be the x component of that original 10 meters per second. The x component of that original 10 meters per second, which will be 10 cos 30 degrees. All right, so 10 times root 3 over 2, or 5 root 3. But let's get some decimals here. So 8.66. Let's do some more math here. Okay, 5 root 3 meters per second. Because I know I'm going to square it in part B, so I don't mind having this square root of 3 there. So part B, how high does it go? So H2. And this one, they want us to use conservation of energy. So I'll set my reference at the original here. So U1 plus K1 equals U2 plus K2. So U1 is 0 due to my reference. So we'll have half mv1 squared equals mgh2 plus half mv2 squared, which I calculated in part A. All right, so the m's cancel. I'm solving for h, so half v1 squared minus half v2 squared divided by g. That'll be the algebra. This can look a little bit nicer. This can be v1 squared minus v2 squared over 2g. Okay, that's just common factoring the half, and then instead of writing a half times it, we can say divided by 2. So just throw the 2 down with the g. All right, so v1 squared says 10 squared. v2 squared is 5 root 3 squared over 2g. So 2 times 9.8. So we'll have 100 minus 75 over 19.6. It's 25 over 19.6. Okay, so we're still using a calculator. There was almost no point in leaving it as 5 root 2. Oh well. 1.3 meters. All right, so there we go. 19. Okay, a mass is attached to the end of a spring, shown, and they give you a nice diagram there. The mass is given an initial displacement of x naught from equilibrium and an initial speed of v naught. Ignoring friction and the mass of the spring, use energy methods to find its maximum speed as well as its maximum stretch from equilibrium. In terms of the given quantities. All right. All right, so let's draw pictures here. Oof, that's not horizontal. Yeah, there's that. That we'll have to do. Okay, we will have the spring here. And then we'll attach it to the box. Okay, I'm just gonna, it's a frictionless surface. I'm just going to erase it all together. There is a surface that it's on and it's frictionless. I just don't want to clutter things up. So right now, it is already stretched. It is already stretched by x naught. And it has an initial speed of v naught. It doesn't say which direction. It will not matter actually which direction. So I'm just going to pick one. We'll say it has an initial speed going to the right. Doesn't matter which direction, because kinetic energy is half mv squared, the speed. It's not velocity. So doesn't matter which direction it is in. And eventually it's going to get to this kind of position here where the spring is stretched even more. And I think that's what we're looking for. This here will be the maximum stretch. That's what they want us to find in part B. They also want the maximum speed. So the maximum speed is going to occur when the block gets pulled back to its rest position. Okay, so that'll be the rest position. So that's when the maximum speed will occur. So let's label things T1. I'll call this T2, because that's actually part A, to find the maximum speed. And then part B is to find the maximum stretch, so I'll call that T3. So part A, starting with T1 and T2, there's no gravitational here, so it's just spring. So U1 plus K1 equals U2 plus K2. So the spring is at equilibrium for T2. And yeah, that's it. So half k x naught squared plus half m v naught squared equals half m v2 squared. All right, so multiply everything by 2. That'll actually cancel all the halves out. Then divide by m and square root. So kx naught squared over m plus v naught squared, and then square root it. Okay, so that's the answer for part A. So the final answer is only allowed to contain variables that are stated in the question. So they tell us m, k, x naught, and v naught. So looks like we are okay. So for part B, we want to find the maximum stretch. So that occurs at T3. So I will go T1 to T3. So, or should I go from 2? No, definitely not. That's, okay, I'm going to go from 1 and 3. So let's see. It will be momentarily at rest when it gets to its maximum compression. So we have 0 there. Okay, so we have half k x naught squared plus half m v naught squared equals half k x 3 squared. So again, the halves cancel out. This time we're dividing by k and then square rooting. So dividing by k is x naught squared and then mv naught squared over k. Then we're square rooting. Okay, so that'll be the answer to B. All right, 23. An An engineer is designing a spring to be placed at the bottom of an elevator shaft. If the elevator cable should happen to break when the elevator is at a height h above the top of the spring, calculate the value that the spring constant k should have so the passengers undergo an acceleration of no more than 5g when brought to rest. Let capital M be the total mass of the elevator and its passengers. Okay, so we have the elevator and its passengers, mass M, and they are a height of h above a spring. The spring has constant k. It's supposed to bring this all to a rest. Okay, so this will be T1. And T2 is after it'll squish the spring. It's not to scale. Okay, so it'll squish the spring and bring it to a rest. So that'll be T2. So my instincts tell me the h equals 0 should be right at the top of the unstretched or uncompressed spring. That's the reference. And we need to calculate k so that at T2, the acceleration is going to be 5g and the acceleration is going to be up because the people are falling down and they're getting come to a stop. So the acceleration is going to be upwards. All right, good. So conservation of mechanical energy. So the whole point is that it comes to a rest. So kinetic energy 2 is 0. I'm going to make an assumption that it also starts free falling from rest, because it doesn't say anything about any initial speed that the elevator had. It just says that the cable breaks. Yeah, I'm going to assume that it starts at rest too. All right, so the spring is not doing anything at T1, so that'll be 0 as well. Okay, so looks like I'll have mg h equals mg h2 plus half k x squared. So we have this thing we need to realize, that x, the amount the thing compresses by, is going to equal to negative h2. Okay, it fell down by h2. H2 is a negative number because it's below the reference. X is always a positive number, so x has to equal to negative of h2. All right, so alternatively, or h2 equals negative x, just algebraically, that works out. So I'm going to replace h2 with negative x. Okay, so we have mgh equals negative mgx plus half kx squared. All right, and we're supposed to solve this for k, I think. Yeah, we're supposed to solve this for k. So looking right now, trying to solve this for k, I'll highlight it. And I don't actually know anything. I don't know any of these numbers. I don't know what the mass is. They just say it's capital M. I don't know what h is. They just say it's h. And I don't know what x is. I only know what g is. All right, interesting. So we're going to need to bring in a second concept here. And that second concept is going to be dynamics. So for the maximum compression of the spring, so at T2 basically, I have a free body diagram here. We have force of gravity, which is capital mg, and then we have the spring's force, which is kx. All right, so the acceleration is net force divided by the mass. But we're told that the acceleration must be no more than 5 g's. And the net force is going to be whatever kx is minus mg over m. All right, so how will this be helpful to us? Is it going to be helpful to us? Well, I'm going to try something. We'll see what happens. I'm going to isolate this for x. So first I'll multiply by capital M, so that'll be 5 mg. And then I will add the mg. Well, okay. And then I will divide by k. Okay, so that's isolating for x, and 5 mg plus mg is 6 mg. So x equals 6 mg over k. And we'll see what happens when we substitute this into the other equation. So substitute it into this equation. We'll see where that leads. Okay, so sub it in to x. Okay, m, g, h. I have no idea what I'm doing, by the way. We're just going to try things. And then this will be 6 mg over k, half k, and then 6 mg over k squared. All right, let's do some simplifications. mgh equals negative 6 m squared g squared over k. Interesting. Plus half k 36 m squared g squared over k squared. Okay, so on this last term here, this k cancels out with one of the k's. Okay, I'll do some more simplification. mgh equals negative 6 m squared g squared over k plus, so half of 36 is 18. M squared g squared over k. So on the right side, we have actually like terms, m squared g squared over k. So let's combine them. mgh equals negative 6 plus 18 is 12. M squared g squared over k. And now we'll isolate for k. So multiply both sides by k and then divide both by mgh. So like m and g cancel with one of the m's and one of the g's. So it'll be 12 mg over k. No, wait, over h. All right, so I think that's it. I think that's the answer. So the wording of this threw me off a little because the wording, it said calculate the value, and this is not a value, this is a formula. This is a whole expression. But to me, it makes sense that it should be an expression because the value should depend on how high this elevator shaft is. The taller the elevator shaft, wait. Does that make sense? Okay, so according to this thing that I got, the higher you fall from, since this is in the denominator, that means the lower the spring constant should be, which is interesting. So you need a weaker spring if they fall from higher. And perhaps that's because if you have too strong of a spring, it will cause them to stop too suddenly and go over that 5g force that they wanted to stay below. Okay, so possibly. But yeah, like it can't be one number for every single elevator, I don't think. It can't be one spring constant for every single elevator, I don't think. It has to depend on how tall the shaft is. And it has to depend on the maximum, like every elevator you go into, there's a sign that says what's the maximum mass it can be. So, like the capacity. So it makes sense that there should be an M in this final answer. I don't think one number should work for every single elevator. So, yeah, I just thought it was weird that they said calculate the value because this is a formula. It's not a specific value.